Is this screen visible?
Yes, sir.
Okay. Okay, so I think we can start now. So very good evening, everyone. I welcome you all to this fourth live session on the course Machine Learning and Deep Learning Fundamentals and Application. So in this particular week, first we'll try to solve the questions of week 3 quiz, and later we'll see some practice problems on support vector machine, that is predominantly the content of week 4. So let's start solving the quiz 3. So you'll find the questions are not in the order same as that is there in the quiz website. So I have taken the questions in such a way that similar questions or concepts related to those questions which are kind of similar, I have gathered them together. Okay. So this is, let us consider this is the first question. So this question states that the MLE of data samples X, which comprises this K number of samples with Bernoulli distribution is. So we have to find what is the MLE for the set of points which basically follows the Bernoulli distribution. So you know that your X, if it is following Bernoulli's distribution, then the EMF, probability mass function. So what would be the probability mass function? Expression of probability mass function for Bernoulli's distribution. It is represented as P of xi and then 1 minus P of 1 minus xi. Now, at the same time, for MLE construction, you have heard in week 3 content, it is mentioned that the points, so these are the points, so x1, x2, xi dot dot xk. So these points basically come from the IID. So this is identical and independent. So being said that the points basically come from the IID distribution. So, and the And we can see that these are independent in each other. So the likelihood function would be the product of all such PMFs for all the points. So therefore, I can write it as from I equals to 1 to k. So it would be P of xi and 1 minus P of 1 minus xi. Now we know that we have to maximize the likelihood to estimate the parameter. So therefore, to maximize the likelihood, so this particular thing is in multiplicative form. So we know that for mathematical stability or for the calculative stability, we have to convert this multiplication into addition. So therefore, what I can do is I can take log. So log of L of P. So I'm taking log of the likelihood. So therefore, if I take log, this multiplication would be converted into summation. And I can directly write it as, let's say, I equals 1 to k. And even I can write it as like xi ln of p plus 1 minus xi ln of 1 minus p. So therefore, we have mitigated the multiplicative functionality by taking the log likelihood. And now we have to maximize this particular likelihood function. So to maximize this particular function, we have to take differentiation. And with respect to what? With respect to the parameter of this particular distribution. And the parameter is basically this p variable. So therefore, what we have to do, we have to take, so it would be derivative with respect to p of this ln L of p. So therefore, if we take the derivative part, so it will give me I equals to 1 to k, and this is xi, and ln p's derivation would be 1 upon p, and then it would be 1 minus xi, and then the derivative would be 1 minus p, and then we have to take derivative of this part also, this inner part also, so it would be minus 1. So therefore, I can write it as xi by p, and this would be 1 minus xi divided by 1 minus p. I equals to 1 to k. And now we know that what we have to do to maximize this, we have to equate this whole thing with 0. And there's a bracket over here. So what I can do, I can, this P is basically independent of this particular summation because this summation is having index I, and this index I basically refers the sample points. So I can write it like this, summation xi, and I'm dropping the subscript I equals to 1 to k. So just I'm writing summation under the subscript is I only. And therefore I can place it like this. So the summation would be summation again I equals to 1 to k. So it would be 1 minus xi divided by 1 minus p. So I can write it like this. Now I can do the cross multiplication. So it would be on this particular side, which would be xi should be summation of xi 1 to k, and then it would be p of summation of xi I equals to 1 to k. Similarly, if I just do it in this particular direction, it would be p summation 1, and the index is running from 1 to k, and then it would be p summation I equals to 1 to k. So therefore, we can see this particular term will cancel. So we are left with summation xi. 1 second, I think someone is trying to join me. So this would give me uh, I equals to 1 to k xi, and then p, and this summation will basically run from I equals to 1 to k. So this basically k times addition of 1. So it would give me p multiplied with k. So therefore, I can write it as p is basically estimated as 1 upon k xi I equals to 1 to k. So now you can see this particular estimated parameter p is basically the mean or the sample mean of this particular distribution of this all sample points. So therefore, the answer is p is equals to 1 upon k summation xi I equals to 1 to k. Hence, MLE is the sample mean of the distribution. So this is the answer. The next question states that consider a single observation X that depends on the random parameter. Suppose theta has the prior distribution. So over here, this is the prior distribution. So if I just rewrite this thing, so f theta of theta, this is basically the prior distribution. So the prior is basically given as lambda e power minus lambda theta, and the conditions are theta greater equals 0 and lambda greater than 0. Fine. At the same time, so this particular thing is basically the prior. This is prior. But over here, the next thing that is, that is x given theta of x is equals to theta e to the power minus theta x. And where the condition is basically mod of x is equals to greater than 0. So this is basically the conditional density. So we have the prior and we have the conditional density. Now the question states that find the MAP estimation of theta. So MAP basically stands for maximum a posteriori probability. So therefore we have got the prior as well as the conditional density. So how can we get the a posteriori probability? Anyone? We have the prior, we have the conditional density or the conditional distribution, so to say. So how can we get the a posteriori probability?
Yeah, can you hear me?
Yes, yes, I can hear
I
you.
think multiplication of a prior and conditional probabilities gives the
Yes,
posterior probability.
yes. So you can get the a posteriori probability through Bayes theorem, and he has actually stated it correctly that we have to multiply the conditional density and the prior so that we can get the posterior estimate. So the actual formula is basically, let's say, if actual formula would be f theta given x of x is equals to f x given theta, sorry, it would be theta of x multiplied of f theta divided by total probability. Now, we have seen from Bayes theorem lectures that this total probability basically does not give any sort of information for classification or any other ML task. So this is basically a scaling factor. So if I just consider it as a scaling factor, so therefore I can write it as f theta of x of theta is it is actually proportional to f x given theta of x multiplied with f of theta. Fine. So now this is basically what the a posteriori probability, not MAP. This is the a posteriori probability. Now we have to maximize this particular a posteriori probability. So over here also we can see the same issue. These factors are basically in the form of multiplicative format. So if I just write the factor, so it is basically theta e power minus theta x, and then you have lambda e power minus lambda theta. So therefore I can even write it as lambda theta e power minus lambda plus x and theta. So this is basically your a posteriori. Now we have to maximize this particular thing, and the form is in the multiplicative format. So what we have to do, we have to uh, take a natural log such that this multiplication thing can be brought down to addition format, and then we can take the differentiation and equate it with 0 to get the maximum point. So therefore, so it's a function of theta. So therefore, what we can do, ln f theta given x of theta, and I can write it as ln lambda theta, then e power lambda plus x theta. So I can even break down it as theta given x theta ln lambda plus ln theta, and then minus lambda plus x into theta. Fine. So now we have to take differentiation. So if I just take differentiation over here, it would give me basically, so d theta of ln f of theta given x of theta is basically, I can still work with the proportional sign as well. So this particular ln of lambda, you can see this particular ln of lambda is basically the decay constant for this particular exponential distribution. So this is a simple constant over there. So as because this is a simple constant and this does not depend on theta predominantly, so therefore we can the derivative would be 0. However, over here it would be 1 upon theta, and then you have lambda plus x. And if I just delete the proportional sign, so we have to take another constant over there. So that constant would be multiplicative constant. 1 second. It would be f of theta given x of theta is equals to k into 1 by theta minus lambda plus x. So now what we can do, we can equate this particular thing, this dd of lambda, this whole thing with equals to 0 to find the maximum point. So therefore it would be k into 1 by theta lambda plus x is equals to 0. So I can write theta is equals to 1 divided by lambda plus x. So this is the final answer. Okay. So the next question is, suppose that x is a discrete random variable, the probability mass function. So over here you can see this is the x is a discrete random variable. So for discrete random variable, the probability function that we get, that is basically called the PMF or probability mass function. So that is what we have seen in the case of Bernoulli function as well, Bernoulli distribution as well. However, in case of Gaussian distribution, as you know, the Gaussian distribution is a kind of a continuous distribution. So over there, the function is basically called the probability density function. Okay. So the probability mass function is given as like this. We have got certain entries, that is for x equals to 0, the probability of x is basically denoted as 2 theta divided by 3 for 1, for 2, and for 3. Now they have given the following 10 independent observations. So over here we have 10 observations which are independent of each other. So for independent observations, the probability is multiplicative in nature. That is, we have seen in the previous case as well. For example, over here, so we talked about the IID, which is basically an independent distribution. So therefore, each and every point, for each and every point like x1, for x2, for xi and xk, for each and every point, the probability density function would be multiplicative in nature. So therefore, the likelihood function would be multiplication of all such cases for all these particular entries. So that is why we have actually taken this multiplication over there. So same way, here they have given 10 independent independent observation. So therefore, the probability would be multiplicative in nature. That we have to keep in mind. Okay. And the x values they have given 3, 0 likewise. Now, what is the maximum likelihood estimate of theta? So what we have to do is basically first we have to construct the likelihood function. So the likelihood function L of theta, and they have given that we have to find the maximum likelihood estimate of theta. So the parameter of this particular distribution is basically theta over there. So therefore, L theta, that is the likelihood function, would be multiplication of I equals to 1 to 10, as because we have 10 such cases, it would be P of x equals to small xi. Now, the small xi's are basically, so the small xi is basically a set of points like 3, 0, 2, 1, 3, 2, 1, 0, 2, 1. So if I just expand this particular form, it would be multiplication of all such points. So P x equals to x1. So x1 is basically over here. X1 is 3. So I can write P of x of 3. Then P of x of 0, P of x of 2, P of x of 1, x of 3, P of x equals to 2, x equals 1. Then you have x equals 0, x equals 2, and x equals 1. So all these are in multiplicative form. So all are in the multiplicative form. So now let us see in the next step. So how many P of x of 3 we are having over here is, this is the first term. This is the second term. So I can write it like P of x equals to 3 whole square. Then P of x equals to 0 comes 1, 2, 2 times. So therefore, again, square P of x equals to 2, this basically comes for 1, 2, 3 times. And then P of x equals to 1 comes for 1, 2, 3 times again. It would be 3. So the corresponding probability functions or the parametric form is basically given as 2 theta by 3 for 0. For third case, it is 1 minus theta divided by 3. Yes. So then you have square over here. For x equal to 0, it would be 2 theta by 3 whole square. Then you have this particular thing is x equal to 2. 2 by 3, 1 minus theta x cube. And then you have theta upon 3 whole cube. So this is what your likelihood function basically looks like. So this is the likelihood function. Now we have to evaluate the maximum likelihood estimate of theta. So over here also you can see that all of these particular functionalities are in the form of multiplicative format. So first we have to take log and such that this particular expression comes to a form of additive functionality. So therefore, let me just copy this thing in the next page. The log likelihood would be ln of L theta, and then I can write it as ln 1 upon 3 plus 2 ln 1 minus theta. Then I can write ln, sorry, there would be 2 in the first part. Then over here it would be, so 3 will come first outside, and then I can even write it as ln 2 by 3 plus 3 ln 1 minus theta. Okay. I think I have missed this particular term. So this particular term would be 2 ln 2 by 3 plus ln theta. And then this is the last term. It would be 3 ln 1 upon 3 ln theta. Now, what we have to do is basically we have to take the differentiation. We have to take the differentiation with respect to theta. So if I just even do some further modification, so you can see that ln 1 by theta ln 1 by theta comes twice. So the coefficients are 2 and 3. So it would be added to 5 ln 1 upon 3. Same as ln 2 by 3, it would be again 5 ln 2 by 3. And then over here it is 2 ln 1 minus theta. And then you have 3 ln 1 minus theta. It would be 5 ln 1 minus theta. And thereafter you have 5 log theta. So now you can take the differentiation d theta of ln L theta. So it would be, so over here you can see that these are the constant terms. So I can write it as, let's say, k, and this would vanish. then you can see that it would be 5 ln 1 minus theta, and we have to also differentiate of also differentiate this particular term 1 minus theta, which will basically give you a minus sign over here, and then you can have 5 divided by theta over here, and which basically equals to 0, so that we can find the maximum point. Okay. So if I just do the simple manipulation, it would be like this. So 1 minus theta equals to theta. So it would be theta equal to 1 upon 2, which is equal to 0.5. So this is the correct answer. So the main thing is that you have to construct this likelihood function. Then after you have to take log. Then you have to differentiate this particular thing. And then finally you have to equate this particular differentiation output with equals to 0. And then you can find the parameter estimate. So in our case, this is theta equals to half, that is 0.5. Okay. So the next question is basically there are 18 points in an axis plane. So over here you can see that your axis plane is basically of two-dimensional axis plane, and the points have been given as 0.8, 0.8. So that means in x direction it is 0.8, y direction it is 0.8. So therefore, like for example, this particular point is belonging in this region. So you can consider that one direction is x1, another direction is x2. So these are the features we have collected from 18 points, and they are from different classes. So for example, these points belongs to class 1, these points belongs to class 2, and these points belongs to class 3. Then, so this is your data set. So your data set basically looks like you have x1, x2, I. And this I basically runs from I equal to 1 to 18, as because they have already told that you have 18 such points. So therefore, x1, x2 करके you have 0.8, 0.8. The second sample would be 1, 1. Third sample would be 1.2, 0, 8. So likewise, so this is the data set that you have. And the label corresponding to the data set is basically given as, for example, 1, 2, 3, 4, 5. These 5 points belong to class omega 1. Rest of the second slab of data basically belongs to class 3. Rest of the data belongs to class 3. Now you have, so let's say if I just randomly draw, so the data set somewhat looks like this. So I am not considering the exact values. I'm just trying to illustrate that how the problem is basically looks like. So let's say this is the class 2. And this is class 3. So this is omega 3. This is omega 2. And this is omega 1. So now at the testing time, you have got another data point, which is basically, let's say, this is data point that you have over here. This yellow one, this is the new data point. Now you have to decide based on the k nearest neighbor with k equal to 5. So you have the algorithm called KNN, which is basically k nearest neighbor algorithm. And where k is equals to 5, so that means within the vicinity of this yellow point, you have to see the most closest 5 points. And then based on the majority voting of the classes of the nearest neighbors, you have to decide that whether the yellow points belong to class omega 1, class omega 2, or class omega 3. So that means at the time of inference or at the time of this new point insertion. So this new point is basically P. So when you inserted this particular new point into the data set, what you have to do, you have to calculate distance from all the data points. From all the data points, let's say from this point, this point, this point, from all the data points. So over here, we have to calculate D of so this point, if I just write it like this, D is basically uh, xi, and x basically represented as by 2 points, x1 and x2, xi. So that is why I'm writing with capital X, and the corresponding label. So this is data and this is label of class. So now we have to calculate the distance between this P point and all other points that is given in this particular data set. So therefore, I can write it as D of x1 comma P, D of x2 comma P, D of x3 comma P. So likewise, we have to calculate all the data points. So let's say 1, 2, 3, 4, 6, 7, 8. So let's say I have to calculate D of x8 comma P. So how I can calculate the distance between this point, this one, and the new point? How I can calculate the distance?
Euclidean distance generally we use, no, sir.
Yeah, it would be Euclidean distance. So therefore, it would be, so just for an instance, I am writing this. So it would be 4.2 minus 4.2 whole square. And then you can write 2.8 minus 1.8 whole square. So therefore, it is 0 and this is 1. So the distance would be 1. So likewise, you have to calculate all the distances in this particular manner. We have to use this. D is basically the Euclidean distance.
Sir, I have a doubt here.
Yes.
Sir, for each point there is a superscript T, no, sir?
Yeah.
What that signifies, sir?
Actually, this particular T, when you are basically doing these sort of operations like this one, when you are doing this analytically, like in pen and paper, so then you know that this is the first dimension, this is the this is the first dimension, and this is the second dimension. So therefore, you just manually pick 4.2 minus 4.2. This is what you are doing manually. But for example, in the case of computers, for the algorithm development side, so there at that particular time, the computer will not be able to understand that what is basically the first dimension, what is basically the second dimension. So what we do something like this. Let's say 4.2, 1.8. You have taken transpose, and then you have also taken transpose over this particular the other data as well. So this is 4.2 comma 2.8 transpose. So this particular transpose will give you this sort of representation: 4.2, 1.8, and then 4.2, 1.8. So there is a function that is called list in Python. So when you pass this particular data dimension in this particular way, so what it will do, the inside algorithm is you first check that what is the first dimension, and then what you do, element wise you do the data subtraction. So the moment you do this particular application like this transpose and transpose, and in many of the cases you'll see when you represent the data through several data points, you have to represent them using column vector. So that is why we first have written the row vector, and then we have written using the transpose. In the coding implementation side as well, in the last week, I had shown that whenever we basically acquired the features from the data, the features should be placed in the column. So that is why you will see that this particular transpose is there. And then when you pass this through you pass this particular arguments through this Euclidean distance function. So then it will do the element wise, first it will do the element wise data subtraction, 4.2 minus 4.2, 1.8 minus let's say 2.8, and then it will do the element wise square. So generally element wise squared is not represented in this way. It is basically a Hadamard product. It's something like this. So 4.2 minus 4.2 would be 0, and then it would be, let's say, minus 1, and then it does Hadamard product like this, 0, minus 1. Now you see for Hadamard product, so the element wise dot product, dot product, when you have to do element wise dot product, until and unless you pass the data in the transposed format, it will not be able to do the dot product. So when you do the dot product, it will be like 0 squared, 0 multiplied with 0, and then the next term would be minus 1 multiplied with minus 1. So that is why it is 1. So this particular notation is basically, as far as the computer algorithms is basically concerned, because anyway, when you'll be applying this particular concepts in computer algorithms or in Python programming, so over there you'll see this transpose thing or the column vector format is the most prescribed format. So that is why they have incorporated the transpose term over there.
Sir, sorry to interrupt here.
Yes.
We have to compute the distance from a new point with all other 18 points given.
Yes.
Among them, we have to take k equal to 5 is given. Sir, what that signifies?
Yeah. I will show you that what 5 data points you have to consider. So the main idea is basically, if I just pictorially show you, let's say this is a case, and let's say you have two classes. For this particular instance, let us consider you have two classes. One class is the green class, and another one is basically the red class. And let me consider this is the new point. And let's say you have to consider k equal to 4. So what you have to do? What you have to do from this particular pink point, you have to calculate distance from all other points in the data set. Then you have to choose 4 nearest neighbor. These 4 nearest points from the new data point. So over here, as you can just pictorially see, if you calculate distance from this point to this point, so from this point to this point, you can see the distance is high, right? But if you calculate the distance from all the points, you can see the lowest distance for 4 particular points would be this one, this one, this one, and this one. So these 4 neighbors you have to consider. So we have to consider those neighbors from which the new point is nearly located, or the distance is minimum. Now, after you choose this particular 4 points, now you see this first sample belongs to class green. Second sample also belongs to class green. Third sample also belongs to class green. Only the fourth sample belongs to class red. So which of the class has highest occurrence? Class green has the highest occurrence. So therefore your decision will be this particular point belongs to class green. Is it fine?
Yes, sir.
Okay.
Yes, sir.
So now, Okay, so now we can proceed with this particular problem. So you know that you have to calculate the Euclidean distance. So beforehand, I have calculated all the Euclidean distance. So just for the clarification, let me just write down all the distance values, and then I will show you that what are the 5 data points you have to consider, as they have mentioned that k equal to 5 is the decision set that you have to consider. So dx1 p, x1 comma p, it is 3.54. d x2 comma p, it is 3.29. d x3 comma p, it is 3.16. x4 comma p, 3.45. x5 comma p, you can calculate as well, but I have calculated freehand, so let me just write down. x6 comma p, 1.22. x7 comma p, it is 1.08. d x sorry, x8 comma p, it is 1. x9 comma p, it is 1.46. the x10 comma p, 1.4. x11 comma p, 1.01. x12 comma p, 1. Sorry, this is 2.6. 13 comma p, so this is 1.72, 1.49, 1.36, 1.06. the x17 comma p is 0.82. the x18 comma p is 1.12. So this is the distance value from p to all the data points. So now you have to consider the 5 lowest distance measures. So the 5 lowest distance values are the 17th one, then the 16th one, then you have this 8th one, you have this 11th one as well. Then the lowest value that I can see is x6, sorry, x7. Okay, so now we can see we have got the 5. So we had to take k equal to 5. So we can see that these are the 5 lowest distance values out of all the 18 distance values. Fine. Now we have to see that what this particular x11 belongs to which particular class. So if I just go to the previous slide, so the first 5, 1, 2, 3, 4, 5. So first 5 belongs to class 1. Then so the next 7 data points belongs to class 2, and the last basically belongs to class 3. So by that logic, the 7th data point belongs to class 2. 8th data point belongs to class number 2. Similarly, x11 also belongs to class number 2. However, now x16 belongs to class 3 and x17 belongs to class 3. So the situation is something like this. You have this new data point. Let's say this is the new data point, and let's say this is the class 2 nearest points, and these are the, let's say, so this is the new point. You have measured the distance from all other points, and these are the lowest distance values for k equal to 5. So this is your all the 5 neighbors. So out of these 5 neighbors, these 3 neighbors belongs to class 2, and these 2 belongs to class 3. So therefore, the class occurrence is higher for class 2. So therefore, your new point P belongs to, or mathematically I can write, the new point P belongs to class 2. So this is the final answer. Okay.
Excuse me, sir.
Yes.
Suppose if you take more value of k.
Sorry,
for
can you
example,
please repeat it again?
Suppose if you take more value of k values are 10, like
10.
10 if
So
you
you,
take, then what will be
okay.
the accuracy?
Okay. So the point is that over here, to define accuracy, let's say, if you have to find accuracy for the test sample, you need the uh, what you call, you need the original label as well. Why? Because you see, uh, you'll only be able to understand that whether your model has predicted correctly or you have done misprediction only when you have the original label known, right? So for this particular case, let's say when I have considered k equal to 5, then my decision is for class 2, right? Now, if my decision is for class 2, and if I change k equal to, let's say, 10, let's say if I increased the number of neighbors, that is k equal to 3. So for that particular condition, I may got some other results as well. But that thing only be checked when you have the original label for that particular unknown, this particular unknown thing. So now what
Yeah,
we have the prediction. So we are predicting this. This is our prediction output,
yes, sir.
but we do not have true output. So therefore, I cannot comment about accuracy. But as per your question, that what would be the optimal value of k for which we can get high accuracy, that totally depends on experimentation. We cannot say that if you take your k in the range of, let's say, 3 to 5, then you will get 99% accuracy. If you take k equal to 10, then your accuracy will be detrimentally dropped. This particular thing can only be ensured via experimentation. You might see in some cases, I will show in the next week through coding, that if you take k equal to 2, you might get good result. If you take k equal to 3, you may get better result. At the same time, if you take, let's say, k equal to 10, your result may, may be detrimental, or the accuracy may be decreased. So
Yes,
that
sir.
particular thing you cannot basically say analytically, because you can see that if you change the number of k, the neighbor that you are considering, that is changing every time. So therefore, the accuracy is totally dependent on the experimentation. By experiment only, you can tell that what would be the accuracy. It may happen that for some k, you are getting very good result. Let's say for k equal to 3, you are getting very good result. For k equal to 4, you are getting very bad result. So that you have to do with experimentation.
Thank you very much, sir.
Okay. Okay. So we have two techniques. That is, one is basically the Partition window method and another is basically the KNN method. So where we have the data points and we basically try to see the distance from the new data point. Now, let me ask you a question. For example, when I write k equal to 5, what is the meaning of k equal to 5?
This is the neighborhood, 5 numbers of neighborhood
Yeah, so that
points.
is this particular k means, yes, you correctly stated that this k equal to 5 is basically number of neighbors. Over here, you can see when I was talking about k equal to 5, I was only concerned about number of neighbors. So this is the first neighbor, second neighbor, third neighbor, fourth neighbor, fifth neighbor. But in case of partition window, the bandwidth parameter. So this bandwidth parameter basically it's something analogous to radius. So this radius means, let's say this is for the partition window case, and let's say this is for the KNN case. And let's say you have this unknown point, and around this unknown points, you have several data points from different classes. So if I talk about, let's say, k equal to 5, I will only consider those 5 points which have the lowest distance. So therefore, let's say this is the first neighbor, this is the second neighbor, third neighbor, fourth neighbor, and let's say this particular value is less than this one, even though the figure looks the opposite way. But let us consider this one is the least value among the all. So therefore, we will only consider those points which are having the lowest distance. We'll choose those k number of points. So this k basically talks about the number of neighbors. If k equal to 5, then I have to choose only 5. If k equal to 3, I have to choose only k. But in case of partition window, let us consider this is my new data point, and these are the data distributions for different classes. Let's say these are the data distributions. Now over here, this bandwidth parameter, as I already have told, that this bandwidth parameter basically talks about the radius of the visualization. So over here, we can consider, if I consider this bandwidth parameter is equals to 5, that means the radius around this particular point, this radius value is 5 units. So what would happen? I will consider a radius 5, a circle with radius equal to 5. So this is a circle, let's say this is a circle with radius r equals to 5. And whatever number of data comes under this particular circle, I have to consider all of them. Rather, in case of KNN, my k parameter was only talking about the number of neighbors. So that means if my k is equal to 5, I will be considering only 5 data points which have the lowest distance. However, in case of partition window, it is basically a circle with radius r equal to 5, which is the bandwidth parameter. And if I construct this r equal to 5 circle, then whatever number of data point comes under this particular circle, I have to consider all the data points to make the decision whether the new data points belongs to class omega 1 or class omega 2 or green class or red class. So therefore, this particular question states that the bandwidth parameter in partition window method determines the number of neighbor consider for the classification. So we can see in case of KNN, it was talking about number of neighbors. So therefore, this particular option is incorrect. The second option, let me see. The second option states that the size of the neighborhood around the test instance. So over here you can see, you can see that you had the unknown data point, this blue one. You have drawn a circle with bandwidth parameter equal to 5, and then you have constructed this particular circle, and then you can see that the number of neighbors. So this is the neighborhood, and the neighborhood comprises a large number of data points. So therefore, you can see this particular bandwidth parameter basically deals with total number of data points or neighbors for bandwidth parameter, let's say BW specified. Someone is trying to join. Therefore, you can see from this particular diagram, you can see that this total number of sample or neighbors is basically specified through this bandwidth parameter. So this also determines the size of neighbor. So that means, let's say if this particular circle encloses 25 data points, so that means the size of your neighbor over here is basically 25. So therefore, it is called this, it is basically measure of size of the neighbor rather the direct number of neighbors. Over here, if you just put k equal to 5, you have to consider only 5 points. But in this case, you cannot take 5 points because it is basically radius of a circle. By that particular radius, how many data points you have covered, that means how many neighbors you have covered, that you have to see. So this particular parameter basically tells you about the size of the neighbor rather than the absolute number of the neighbor. So therefore, this is the correct answer. And this window techniques has no relation with dimensionality of the feature, complexity of the classifier. These are not directly related with this particular Partition window techniques, because dimensionality related things you'll see in the subsequent weeks. That is, there is a technique called PCA, principal component analysis. Over there, you'll see what is basically meant by dimensionality reduction and all. Okay. So the next question is the disadvantage of using KNN as classifier. So we already have seen that for KNN, if you have a data set something like this, if you have a data set something like this, let's say you have 3 different classes, and at the time of inference, you have the data set. Now you have an unknown data point. You have to place that particular data point, and then you have to calculate the distance of this data point from all other data points. So you can consider that for just solving this particular small problem where we had only 18 data points, I have to calculate this Euclidean distance for 18 data points, and I have to uh, allocate a memory for each of the distance values, because I have to memorize all these data points, all these distance values. Then only I will be able to gather the lowest 5 distance values, as because I have written k equal to 5. So that means for all the 18 data points, I have to first calculate the distance. Then I have to create a separate memory so that I can store all these distance values. And then based on the lowest 5 case or lowest 10 case, if you choose your k to be 10, then we can take the classification decision that whether the new point belongs to class omega 1 or class omega 2 or class omega 3. So you can understand that when you will be dealing with large data set means you have large number of samples. Let's say you have 70,000 samples and you have brought a single data point to classify using KNN with k equal to 5. Now you can consider that from that new data point, you have to calculate 60,000 such distances. Then you have to allocate a separate memory in RAM to store all those distance values. And then you have to take decision. That means you have to sort the distance values in such a way that the 5 or 10 lowest distance is basically measured, and then you can take the decision. So that means when you will be dealing with larger data set, then KNN will have some issue related with the computational complexity. So for large data set, KNN will have computational problem, because you can understand you have lots of data, you have to calculate the distance, you have to store them in memory in RAM. So this is very much computationally cumbersome process. But once you calculate all the distance values, because that means you can see the time taken by this algorithm will be higher as you increase the number of data, because you have to calculate all the data point distance. So once you calculate all the distance values, then what you have to do, you have to arrange the distance values in ascending order, and then you can take, let's say, k number of lowest distance, and then you can do the classification. So far as the classification is concerned, KNN will have no problem doing classification. It will only have certain issues related to computational problem or time taken by the algorithm, time taken by algo will be high. That is the only drawback of KNN for larger data set. But so far as the classification accuracy or classification perspective is concerned, KNN will have no such issue. It will be able to classify well because the algorithm is generalized. So therefore, this failing while handling the data set, this particular line is not solely correct. Because so far as the because for any classifier, the main target is basically to classify samples. If you are able to classify the samples pretty well, then it does not, then you can say that the classifier basically works very well. It may take some substantial amount of time to do the classification, but that does not mean that the KNN algorithm will fail every time when it will handle the large data set. So therefore, this particular line is not solely correct. It would have been correct if they have given the reasoning like this: for larger data set, KNN takes larger amount of time, larger amount of computational time, or inference time, or test time. So you can see all these other terms as well: inference time or test time. In case of KNN, let me just write another statement. In case of KNN, there is no need of training. And why there is no need of training? Because this particular technique has no parameters, because this is a non-parametric method. So because this is a non-parametric method, and it just has to calculate the distance value from the new point to all other points. So KNN does not require, so there are few things that you have to that you have to keep in mind. One is, in case of KNN, there is no need of training because this is a non-parametric method. So you do not need any sort of training. What you will have, you have a data set, you bring a new data point, and then what you do, you calculate distance from this new data point to all other data points, store them in a memory. You can store them in ascending order, take first k smallest values, and then you take the decision. That is what you do effectively in case of KNN. So therefore, there is no need of training because it is a non-parametric method. And the third thing is basically the same. You just have to calculate distance. So the second technique, second statement they have given is fails while handling small data set. So if handling larger data set was, there is no problem as far as classification accuracy or classification performance is being concerned. So over here, in case of small data set, you have very small number of small number of data points. So therefore, if you bring a new data point into the data set, you'll have to calculate very small amount of distance values. Then the RAM requirement would be very small, and the classification accuracy, as far as classification is concerned, there is no issue. So therefore, this particular statement is totally incorrect, that it fails for smaller data set. Rather, it basically works for smaller data set very well. Okay. Then you have the last one, that is training is required. So already I have told you, in case of KNN, this is a non-parametric method. So you have nothing to learn from the data. So therefore, there is no need of training of using KNN method. So this is also incorrect. Now we have to see the third statement, that sensitive to outliers. So can anyone of you tell me that what is an outlier? Okay, let me give you the answer in a pictorial form. Let us consider we have two classes. We have binary classification problem. The classes are cat and dog. And from each cat and dog, we have taken two features. One is height of the cat, another is height of the animal and weight of the animal. So let me consider that generally cats are very small. So therefore their heights are small as well as they are of less weight. So if this particular axis is weight and this particular axis is, let's say, height, then the cat class, majority of the cat class will be sitting in this region, let's say. So this is the cat class. And let us consider major amount of dogs that we'll see. They have they have higher heights than the cats, as well as they are larger in weight values as well than the cats. So therefore, the height and weight both will be, let's say, large. So let's say this is the data representation for dog class. Okay. Now we have to see that what is an outlier. Now let us consider in the training set, the dogs that you had were mostly, let's say, Indian street dogs. You have, let's say, golden retriever, and let's say you have husky. So they are of, let's say, their order in height and weight are almost similar. In case of golden retriever, husky, and let's say Indian street dogs. And cats are like, you can consider Indian street cats as well. Now, let's say you bring a new dog that is of some other foreign breed like Chihuahua. So the Chihuahua dog is basically, they are this, that particular new is, let's say, residing over here. 1 second. So this was for dogs. This was for cats. And this is the new data point. So this is the new data point. So the true level of, let's say the data point name is P. True level of P is dog, and that is of, let's say, Chihuahua class. And you have been asked using KNN, you have to determine that whether P point belongs to cat or dog. So what you will do, you have to calculate the distance from all the points, here also from all the points. Then you have, what you have to do, let's say I consider k equal to 5. You have calculated all the distances. You have stored all the distances in, let's say, ascending order. Then let's say for k equal to 5 means you have to consider 5 most nearest neighbors. So the most nearest neighbor would be this one, this one, this one, let's say this one, and let's say this one. So this highlighted, pink color highlighted neighbors are found as, they belong to cat class. So your prediction is cat. But your original class, that means that particular dog, originally that particular animal belongs to originally dog class. But your KNN basically predict it as cat. And this is what outlier means. Outlier means those data points whose properties, so this is actually a dog. It should have been lying over here, but you can see the height and weight, it is more likely towards the cat class. So that means even though this is a dog, majority of the property of that dog is similar to the property of cat. So these sort of data points which have some sort of notion of misclassificability, so those points are called the outlier points, which can bring the misclassification into the testing, into the inference time or the testing time. So over here also you can see, even though this particular point belongs to a dog class, its properties such as height and weight, it is quite less than the general dog classes. So therefore, even though this is a dog, the KNN classifier will be biased towards cat class. So this is what the so this is where you will get the misclassification. So over here you can see that you have done misclassification. So that means for such points, 1 second. Okay. So what I was telling was, so for this particular cases, for this particular outlier case, you can see that your classification accuracy will go down. So that means these sort of classification algorithms like KNN, they are totally sensitive towards the outlier data point. Because if you have an outlier, your classification accuracy may go down. So therefore, this particular option is correct so far as the classification point of view is concerned, because the outlier may lead to misclassification. So that is why this is the correct answer. Okay. So the next question is, which of the following statement is true about KNN classifier? So over here, you can see odd number of K is preferred over even number of K values. So this has logic, because let's say this is your unknown data point, and let's say you choose K equal to 2, and in the second case you choose K equal to 3. So let's say you have the nearest data points like this. Okay, so this is what your data point basically looks like in this particular case. So this is the unknown data point. For K equal to 2, you will choose only these two data points. However, for K equal to 3, you will choose this 3 set. So now you can see, if you choose K equal to even value, so you can see that if you do the voting, so over here, the point belongs to omega 1, the point belongs to omega 2. So there is a tie. It either belongs to, so this point P is near to class omega 1 for this case. This point P belongs to class omega 2 for the second case. So therefore, you'll not be able to say that whether P belongs to omega 1 or omega 2, because the voting is now, it is like a tie situation. However, if you choose K equal to 3, in those cases, you might occur into this particular triangular pattern, triangular kind of thing. So in this particular pattern, you can see that the 2 points, these two points belongs to class omega 1, whereas this red point belongs to class omega 2. So therefore, if you do the majority voting, or if you try to see that which class is basically occurring more frequently, so therefore you'll see that this omega 1 class is basically occurring more frequently. So therefore, this particular black point will belong to class omega 1. So if you choose K equal to 3, if you choose odd number of K, then you might avoid the tie situation for class to find the class occurrence. So that is why we prefer the odd value of K rather than even value of K. In case of even value of K, you might get a 50-50 chance. But in case of K equal to odd value, then you can actually uh, uh, get some situation like this, and you can do the majority voting to get the class output. Okay. The second statement is, does more computation on test time rather than train time. So we already have told you that there is no requirement of training, as because this is non-parametric method. Rather, at the time of testing or at the time of inference, so that we have already written over here, at the time of testing, what you do, you have to calculate distance from the new point to all other points. So which is basically a cumbersome process if you have large number of data in your data set. So therefore, you need a huge computational complexity, or the computational time will basically exponentially grow if you have large number of data points. So these are often called NP-hard problems as well, but I'm not going into the data structure related issue. But this is a very common problem in case of this non-parametric machine learning methods. The computational time basically grows exponentially when the amount of data grows up. Then it works well with high dimension. It is not the case, because when you have higher dimension, what do we mean by higher dimension? So over here, like we have considered height and weight as the features. Instead of taking two features from cat and dog, we can take, let's say, thousands of features. So if I take thousands of features, my dimension would be 1000 dimensional. I will be in a 1000 instead of, like in this particular case, we were in a 2-dimensional space. Rather, if we take 100 such features, will be in a 100-dimensional space. Now you can consider, if you are placing 2 data points in a 100-dimensional space, what happens is, this is a rule in statistics as well, that if you have higher and higher dimension, what happens if you try to calculate the distance from these 2 points, they would be uh, almost equally likely to have similar distance from all other points. Let's say you have a point over here and you have 2 other points. So this is the new point. So let's say this is the new point. On one have another point for, let's say, class omega 2. From another side, you have a data point for class omega 1. What will happen? You'll calculate the distance between from this point to this point, from this point to this point. When you have larger and larger amount of dimension, these distance values, irrespective of their positions, may blow up to same order. So therefore, detecting the class samples based on the distance that you acquired in the higher dimensional space, that is not quite relevant, because there what happens is, there is a very popular theorem is there, that is, all points become almost equally distant in higher dimension. So therefore, if you calculate the distance using Euclidean distance formula, there you will see that for both the cases, let's say for D1 and D2, you will get similar type of value. So in those cases with higher dimension, KNN basically performs very, KNN is not a good classifier for those cases, for higher dimensional data classification. So we do not use, we try to avoid KNN there. The optimal value of K for KNN is highly independent of data. But this particular term would be, this would be true had they been given like it is highly dependent on data. Because earlier also I told you that what would be the optimal value of K for which you will get the highest accuracy, that is something you cannot directly predict, because it is totally dependent on the data. So you'll not be able to, basically predict or do the correct classification over there. So this is totally dependent on data. You have to do certain experiments. Let's say k equal to 4 के लिए कितना आ रहा है, k equal to 3 के लिए कितना आ रहा है, the accuracy values, and then you have to see, okay, let's say for k equal to 10, I am getting the highest accuracy. So your idea would be, for this particular data set, I have to take k equal to 10 such that I can get the highest accuracy. So this is totally based on experimentation. So I cannot say that it is independent of data. Rather, it is purely dependent on data. So by that logic as well, so this particular answer is also incorrect. So you have two correct answer. And let me tell you, in the quiz part, when you'll see the options are given just in front of the options, they have been given round structures. There you'll have single correct options. And if they have box-like structures, they may contain, I'm not definitely saying that they will contain, they may contain more than one correct answers. So that you have to keep in mind. So let's say in case of NPTEL, at least if you pick one of the correct answer, you will be, I think, given the partial marks. Partial correct will be evaluated partially. If you choose both of the options, if you take both of the options, then you will get the full marks. That is the fund. So you be cautious about the fact that if the options have this circular structures before them, then obviously there is a single correct answer. If you have square-like structures, then there might be more than one correct answer. Okay. Okay, I can first solve this particular answer. So this is also related with KNN. So what happens when k is equal to 1 in case of k nearest neighbor? So if I just again take the previous example that you have, let's say, height and weight, and you just plot them, cat and dog classification again. Okay. Now you see that you are considering k equal to 1. That means you will be taking decision based on the lowest distance value. That means you will be only considering single data point. Let's say in the test time, your data is residing over here. Your data is residing over here. You will just see that this particular sample has the lowest value. So I will be seeing that what is the class of this particular blue point. So that is cat class. So my pink point will also belong to the cat class. So you'll be checking only the nearest neighbor. That is only the single neighbor that you will be considering. So for these sort of cases where the new data point has similar property as of the original training data set, there you'll be able to classify it very well. But as we already have seen that, let's say you have an outlier. So these are for dog and these are for cat. The original that is true is, let's say, dog. But now what you are doing, you are only trying to see that I will check the lowest distance. So for this case, your classification output would be, that is prediction would be cat. So that means when you just see single data point, there is a huge risk that just by seeing a single person, you should not have any preconceived notion. You should not bear any sort of preconceived notion. For example, there are two kids. One sits in the first bench of the school and another is a backbencher. And let's say a new student came and he basically sits beside this first bencher. So, but let's say his marks is in the exam, he got 50 and this guy got 80. So just by looking at glance that these two people are sitting beside each other in the first bench, you might think that this guy is also maybe the topper of the class, maybe one of the toppers of the class. But perceiving that notion or classifying that particular guy to the topper class may not be correct, because you are only seeing, you are only taking decision based on the single sample. So this is what I'm trying to infer, that if you just try to see a single neighbor, there is a high chance at the time of while dataset construction, you'll hardly see any sort of error. But when you'll do the testing, at the time of testing, your model will have pretty hard time in doing classification properly, because there is a every possibility that for such cases, your model just by looking at a single data point, it will do certainly misclassification. So these type of problem, that means at the time of dataset creation or the uh, pre-testing phase, it is doing good classification. But at the time of testing or inference time, when it has to calculate all the distance, then store the distance ascending order, and then do the prediction, at that time, it is not able to work properly. So this kind of problem we have seen already, that let's say this is your loss versus model. So this is, let's say, loss versus model complexity is basically concerned. Complexity is concerned. So over there, you can see that at the time of pre-training, pre-testing, and this is the testing. At the time of pre-testing, your loss was very less, but at the time of testing, his loss is very high. So that is what we are encountering over here, that at the time of pre-testing, as because you are just seeing based on the nearest data, you'll obviously see that this particular point belongs to cat. Again, if you just see these 2 points, you'll see these, they belong to cat class, because you are only seeing a single point, single nearest point, and you are doing the classification. But at the testing time, if you encounter some sort of outlier, just by looking at a single data point, you will not be able to classify it properly. So your test loss will become higher and higher. So this particular problem we have seen already. This is called overfitting problem. Underfitting means your test accuracy is also high, pre-test accuracy is also high. That means your model is not able to learn anything. But that is not the case. You can see initially your model is able to learn everything. That from this particular cluster, you can see all the data points will be cat only. From this particular cluster, all the data points will be dog only. But at the time of testing, your model may do misclassification. So therefore, you can see that underfitting is not the correct answer. Similarly, high testing accuracy. You can see you are doing misclassification. Then how come you can get high accuracy? So therefore, this high accuracy is also incorrect. So by same logic, all of the above will also be incorrect. So as we can see that we are incurring overfitting. That means at the case of pre-testing, your accuracy is pretty low. You are doing very good classification. And at the time of testing, you are doing a pretty bad sort of classification. So therefore, you can say that you are encountering a overfitting scenario. Okay. And the last question, it states that if the number of data sample becomes very large, so what would be from the above 4 statements? So have any one of you approached this particular question? Yes,
No,
anyone?
sir. Could
Okay.
not guess actually, and could not get time to go through the theory and all.
Okay. Okay. Okay, fine. So let us just check what are the terminologies they have referred to. One is Bayesian estimation. So we know in case of Bayesian estimation, what we try to do, we try to find the a posteriori probability. So it is something like that. So in the second problem, I guess. 1 second. Yeah. So in the second problem, we had prior and conditional density. So if I just go to this slide, yes. So in case of Bayesian estimation, we try to calculate the a posteriori probability. That is, if theta given x, we try to calculate, and let me equate that with if x given theta and f of theta. So this is what is called prior. This is what is called class conditional probability density. And this is your a posteriori probability. Now, this prior, this x is basically the data. And theta is basically parameter of distribution. So now you can see, just tell me that this particular expression, this class conditional density, uh, does it depend on the data component?
Yes, sir.
Yes. So clearly you can see that this particular thing depends on data. Similarly, this particular term, the a posteriori probability, also depends on x, because you are given the feature, you're trying to predict the class, that is theta, or the parameter. At this prior distribution, f of theta, it is solely dependent on the parameter of the distribution. So what do we mean by the parameter of the distribution? Let's say you have a Gaussian distribution. So the parameter, and let's say this is a zero mean Gaussian distribution. So therefore your mean value is equals to 0. You have only left with the parameter, that is the variance parameter. So this f theta, it does not depend on the data part. It is the distribution, and it is basically dependent on the parameter of the distribution. That is, if sigma square is higher, then the distribution would be flatter. If sigma square is low, then the distribution would be very sharp, like this. So this is sigma 1 square, this is sigma 2 square, where sigma 2 square is greater than sigma 1 square. So that means clearly you can see f of theta, it totally depends on the parameter of the distribution, and it basically gives the shape of the distribution, whether it would be flat distribution, whether it would be peaky distribution, something like that. But it has no component of x, that is the data. Now I'll try to infer something from the question. That is, if the number of data samples becomes very large, and let me just focus on this particular term. This is called prior. Prior means something like that कि पहले से ही हम लोग कुछ सोच के रखे हैं इस चीज के बारे में. That means a prior knowledge. That means, for example, if I just infer to this particular example, जो लोग first bench में बैठते हैं, all of them are topper. So this is something like that. This is called a prior notion or prior knowledge. So this prior knowledge, as because it does not depend on data, that means the prior knowledge has some sort of bias. So over here also, I just told you, like this particular guy, this pink colored guy is getting 80% marks, and this guy is getting 50% marks, just because they are sitting together in the first bench. Assuming or based on the prior knowledge, if I just try to understand whether this particular guy belongs to one of the toppers of this particular class or not, it is very much difficult, and it is erroneous actually, because I have already conceived that those who are sitting in the first bench, they are the topper of the class. So this prior, based on the prior, if you take the decision, that would be totally incorrect. So that is why we need class conditional density, and which depends on data. However, prior does not depend on data. So the component which has nothing to do with data, if you are just taking help of the prior to classify, that would be purely wrong classification. So that is why what we do, we take two components, one component which depends on data, that is class conditional density. And to support this, we use prior with this. We use a joint uh, operation, something like that. We could take multiplication or some sort of weightage of prior. So if you have very less amount of data, there you can say that I need some sort of a prior, because let's say you have in a data set, you have, let's say 10 number of samples. You have very small amount of sample. If you see any sort of small video related to machine learning and deep learning, like in YouTube, if you see, first thing they will say that machine learning and deep learning needs lots and lots of data to train the model. And in such case, if you have very small amount of data, let's say in a data set, you have only 10 data points. So in that particular case, from 10 data points, you'll not be able to learn much. For those cases, you have to have some sort of prior, because that prior may guide you well. It may not as well. That is why I'm not putting any sort of definite statement over there. But taking the help of prior in the smaller data set would help you. It might help you. But let's say you have a data set in which, let's say you have millions of data. That means ample of data you have. So if you have ample amount of data, considering prior distribution over there is meaningless, because as you have larger and larger amount of data, you have enough data to extract features, and from those features you will be able to learn something out of the data. And for those cases, it is always preferable that even if you have certain prior, हम लोग बोलते हैं कि prior को side में रखो, only you have the data, from the data you try to learn everything. For those cases, if you have larger amount of data, the importance of prior diminishes. The importance is very less over there if you have larger amount of data, because you can learn everything from the data itself. So for those cases, we do not consider about f theta. So for larger data, for larger data size, the f theta given x, that means the posterior probability almost becomes same as x given theta, that is class conditional probability. Okay. And now, what is MLE? MLE is maximum likelihood
So please
estimation.
repeat that sentence. If large size of data is there, then the probability.
Okay. So for larger amount of data, what I was trying to discuss is basically you have had this particular equation where f theta was solely a prior knowledge. This class conditional probability was a data driven term, and so as the posterior probability. So now, if you have larger amount of data, so there you have larger amount of data, you can extract several amount of feature, and from this feature you can learn about the data set. For those cases, the importance of prior is very negligible. So therefore, for larger data, the posterior probability, that is f theta given x, becomes almost similar. So this is almost similar to the class conditional probability. So that is why I have written f theta given x.
That is class conditional probability density. This one.
Yeah, that is class probability density. This is density. Okay. So this is one inference. Just keep in mind that posterior probability becomes almost similar as class conditional probability. Fine. Now, this posterior probability is also called the Bayesian estimate. Bayesian estimate. So these are the different nomenclatures. It is called posterior probability. It is called Bayesian estimate, etc., etc. And now let me try to draw some analogy of this class conditional probability. So this class conditional probability is similar term of the likelihood function in case of MLE. And how this and why this is similar to the likelihood function of MLE, that I can give you one example. Just go to the previous question. Yes. So over here, you can see that you have you have to find the maximum likelihood for theta. So theta is the parameter of the distribution that for that you have to find the maximum likelihood. And for that, we were first trying to extract the likelihood function. So that is L theta. And how we are calculating L theta? We are considering that all of them are coming from IID, that is independent, that is identical and independent distribution. So that means all of the probability values would be multiplicative in nature. And that is why I equals to 1 to, let's say, 10. So over here we had 10 such points. So therefore I equals to 1 to 10. And what was the probability value that we are talking about? The probability value is x given xi given theta. And how I can defend this particular term? So see, we were putting the value of p x equal to xi. That means we were putting, let's say, p x equal to 1. And what is the parameter of the distribution? That means given that parameter, we are basically, given that parameter theta, we are basically trying to evaluate the probability. So that parameter was theta over there. And this is parameter, and this can be written as they have given for x equal to 1. So this is basically p x equal to 1 given theta. So this basically corresponds to theta divided by 3. That means given that particular parameter, we have to see what is the probability for a sample x equal to 1. So this is basically the likelihood function that we are talking about. So the structure of the likelihood function, you can see, I can also write it like this in general format. It is px given theta, which is similar to class conditional density. So that means this is just a game of nomenclature. So the class conditional density is a similar term as the likelihood function. So now we have got the another nomenclature for class conditional probability density, that is, this is likelihood function or likelihood density. So that means this side is called Bayesian estimate. It can also be called the posterior probability density. This side can be called as class conditional probability. Also, it can be called as likelihood function or density. Now try to match the options. So the first option states that if you have larger amount of data, Bayesian estimate is worse than MLE. So this has no relation, frankly speaking. MLE tries to extract the parameter of the distribution. You know the shape of the distribution, but you do not know what is the value of the parameter. For that, you use MLE. But Bayesian estimate, that estimate is basically the posterior probability through which you try to get the class identity. So that means this particular statement has nothing to do with whether it is worse with MLE or it is better with MLE. It is not something like that. Same, the third statement, Bayesian estimate. Sorry. So the next statement is maximum likelihood estimates are slightly bad. This is also incorrect because you can see in case of maximum likelihood, if you have larger amount of data points, So your log likelihood depends on data, right? Your likelihood function or log likelihood function, if you just take log over here, so that would be log likelihood. So I can interchangeably uh, rename it as log likelihood as well. So if you take likelihood function or log likelihood function, you can see that depends on the data. So if you have larger amount of data, you'll be able to learn more. So that means if you have larger amount of data, your MLE should give you better result over there. So therefore, stating MLE estimates are slightly bad, this is also incorrect because it is dependent on data. If you have higher amount of data, that means it is better. The estimate would be more closer to the original one. But as far as this particular MCQ question is concerned, the third statement is Bayesian estimate performs same as MLE. So over here, this is the inference that I was trying to draw, that this was the Bayesian estimate. For larger amount of data, Bayesian estimate is proportional to class conditional density, which is the likelihood function. And now, if you have larger amount of data, your MLE will perform very well because you will get very close estimate as the original one. So that means if you have larger amount of data, your likelihood estimate or MLE estimate will be performing very good. That is why I'm putting the upper arrow sign. And from this particular expression, you can see that posterior probability is proportional to the likelihood function or class conditional probability. So that means if your estimate is good at this side, and as it is proportional in nature, so estimate at this side will also be very good. So that means their Bayesian estimate and likelihood estimate will give you similar sort of result. So that means their performance will be similar. So that is why this particular answer is the correct answer. Any query?
No, no, sir. It's okay. To somewhat, it's okay as you have written in the red form Bayesian estimate and parallel. It is proportional to likelihood function density. So in that case, it is same as Emil. That fourth option will go. I feel like that.
Yeah. The reasoning is more like you have got this particular expression. Now you have to see that start with the second statement. They have stated maximum likelihood estimates are slightly bad if you have larger data point. So maximum likelihood, that means this likelihood function, which is all the expression is like x given theta. It is dependent on x. Now you have larger amount of x. So if you have larger amount of x, you have lots of training samples to understand. If you have larger amount of x, then your understanding will be far better. Let's say you have two data set. In one data set you have 10 samples. You want in another data set you have, let's say, 1,000 samples.
Yes.
So for 1,000 samples, your learning will be better rather than 10 samples. So that means log likelihood estimate, MLE estimate will perform better if you have larger amount of samples. So that means this particular line is incorrect. Now, as you got that you have larger amount of data, so that means your likelihood estimate would be high or likelihood estimate would be more correct. So that means now you come to this particular expression. So as this particular likelihood function estimate is accurate, so that means your posterior probability or Bayesian estimate will also be accurate. That means their answer or their results would be very much similar. And as you can see that f theta's importance has been gone down. It has no importance. Therefore, they are quite similar to each other. And that is why the Bayesian estimate performs same as M. This is the reason. Okay, so any further query?
Sir, beginning 5 minutes I can go through. I'll join late. So the
So
beginning
I
5 minutes.
I will be uploading the video in YouTube. So anyway, you can check the video.
सर उसका लिंक कैसे पता करूं? अर्कर है
अच्छा
करके।
अच्छा अच्छा मैं दिखा देता हूँ. So
हाँ
1 second. So what you do, go to the website.
यस
Let me increase. Okay, so in this particular side, in the left hand side, you can see there is a tab called problem solving session.
यस यस 23 वाला सर कुछ कुछ तो है, मैं देख रही थी 23 वाला असाइनमेंट 1 2 3 4 सॉल्व वाला दिया गया है, तो इसको
हाँ
मुझे चेक करना पड़ेगा।
हाँ, ये मैं आज ये क्लास होने के बाद आई विल बी डाउनलोडिंग द वीडियो एंड इमीडिएटली आई विल अपलोड. और मैं यहाँ पे जो
सर
यहाँ पे लिंक पेस्ट कर.
ये वीक 4 वाला में आएगा?
हाँ, ये वीक 4 वाला में आएगा.
हाँ सर
एक्चुअली हम लोग एक वीक लैग में चल रहे हैं क्योंकि
यस 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 फिफ्थ वाला
अदरवाइज
तो
विल नॉट बी एबल टू सॉल्व द क्विज. अगर
हाँ
सेम पेस में चलेंगे, एज बिकॉज
हाँ
क्विज लाइव रहेगा, विल नॉट बी एबल टू सॉल्व द क्विज. नहीं तो क्या होगा कि हम लोग क्विज इवेल्युएट होने के पहले ही आंसर कर देंगे. तो दैट इज
हाँ
वाई हम लोग एक वीक लैग में चलते हैं.
Sir,
ओके
excuse me,
सो
sir.
यस 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 प्लीज.
You had gave very good example, sir. Students who are sitting in the front bench may not be. Hello.
हेलो यस प्लीज.
You have given very good example, sir.
ओके ओके थैंक यू. थैंक यू.
That is, students who are sitting in the front bench may not be listening. That is, from that we can understood this whole topic, sir. Thank you, sir.
Okay. Actually, see, this particular subject is pretty. When you have good intuition, then your understanding will be far better. If you just do some sort of mathematical, if you just treat in as a mathematical subject, you will see there are lots of derivations will be there, but solving those derivations would not be that helpful if you are not able to understand those things intuitively. Because anyway, आप ये कोर्स करने के बाद मेजर मेजर मोटिव ये रहेगा कि इसको आइदर पाइथन में इम्प्लीमेंट करें या मतलब रियल टाइम एप्लीकेशन के लिए यूज करें. So for that thing, the more you get the intuitive ideas, the more stronger will the concept will be. Otherwise, it will be a mathematical course only.
Okay, sir. Thank you, sir.
Okay, so I will be uploading the slides as well in that Google Drive link. So we have solved the week 3 part. I have taken some questions related to the topics that we have covered in
सर इसका
week.
डिस्कस सॉरी सर इसको डिस्कस
Yes,
किया
yes.
क्या आपने? फाइंड द स्केलर प्रोजेक्शन ऑफ वेक्टर b इक्वल्स टू लेस देन -3. आई कुड नॉट
कहाँ पे समझ में
अभी
नहीं
अभी
आया.
जो अभी तो था सर, नेक्स्ट वाला स्लाइड पे जो आपने दिखाया.
अच्छा हाँ, ये स्लाइड्स एक्चुअली मैंने कुछ प्रैक्टिस प्रॉब्लम लिया है. So I thought of solving week 3 quiz, and then I would have show you some questions related to the current week. This may not be the same as the questions that are there in the live quiz.
असाइनमेंट
So this particular thing is basically taken from the concept of SVM part. So find the scalar projection of B onto A. So this is something like this. You have two vectors. We have to take scalar projection of B. Let's say B is located like this. Let's say B is located like this. And A is another vector A is another vector like this. So for scalar projection, what you do is basically you have to take. So we have to take scalar projection of B on A. That means it is something like this. We have to see the projection of B on A. And what we basically do, we first try to create the unit vector along A cap. We try to find unit vector along A vector. So that is basically this is simple vector algebra. So this is A divided by norm of A. And then we know from high school mathematics that projection of two vector means dot product. So that means we have to calculate the dot product of B and A cap. That is the unit vector along A. So I can write it like this: B dot A dot norm of A. So if I just do B dot A, so this is -3, 2, and this is 1, 1, and norm of A means 1 square plus 1 square. That means this is the magnitude of the vector. And dot product means -3 into 1, so that is -3 plus 2 divided by √2. So this is -1 upon √2. So this is what the scalar projection basically evaluated as. Then the next question states that there is a feature vector represented as 1, 4, 3. That means now in this particular case, you have a three-dimensional feature 1, 4, 3. What is the distance of the feature vector from this separating plane? And you have an equation of a plane. So you have seen something like this in the week's lecture. For example, this is a plane. This is a plane which has an equation that is x1 plus 2x2 minus 2x3 plus 3 equals to 0. And you have a point, let's say this is the point, which is as x equals to 1, 4, 3. You have to calculate the distance of this point to this plane. From this plane, what is the point? What is the distance of this point? So this distance is basically, let's say this is d. So from this week's lecture, we have seen that how to calculate the distance. You have been given the, sorry, you have been given the what you call planes equation. So from planes equation, if I just write in terms of traditional machine learning structure, that everywhere you'll see we write W transpose X plus W naught equals to 0. This particular equation we'll see everywhere in machine learning textbooks or even in this lecture series as well. So what is this W? What is this particular W means? This is basically means the weight of the weight values of this particular equation. So that is, I can write this W transpose as 1, 2, -2. And the
Sir,
W naught, yes, yes.
sir, this in this plane it is red color and the point is blue color. So it feels like that the point is lying on this plane. Okay,
No,
okay.
it is like in 3 dimension, you can, let's say this is the plane and the point is like somewhere lying over here.
Space
It is
3D.
not, it is in 3D. So now you can think that this is the plane
Distance.
and this is the point. So you are trying to calculate the perpendicular distance from this particular point to on this particular plane.
Plane
This is
3D.
what you are trying to evaluate. Okay. So this weight value is basically the coefficients of this feature value. So that is 1, 2, -2. And this particular term is basically called bias. And this bias value is what? 3. So this is this is as far as traditional machine learning point of view is concerned. We can write it like this. And even I can write these features. As you can see that you have three-dimensional features. So X is basically X1, X2, and X3. Now you do this particular operation. So this is just for illustration part, W transpose X plus W naught. What you will get? So this is 1, 2, minus 2, and you have X1, X2, X3, and then you have W naught equals to 3. So it would be 1 into X1, that is X1 plus 2X2 minus 2X3 plus 3. So now you can see your W transpose X plus W naught as all of these notations are basically kept in mind uh, on the fact that we'll be implementing all these algorithms on computer. In computer, uh, you have to process data in either array format or matrix format. So that is why you will see everywhere they use this transpose kind of thing, which is a matrix operation or a vector operation. So that is why you'll see these kind of uh, uh, styles that is basically preferred in machine learning books or any sort of machine learning
Yes,
lectures.
yes, sir. In math work also it is done like in maths, MATLAB. Also we do
In
like
MATLAB
transpose.
also, yes.
Yeah, yeah.
In
So
MATLAB
then in
also. So
uh,
you can also do this particular operation. Na? So what I have written over here, you can also do it in
yes,
MATLAB as well.
yes, yes, yes.
So, so far as the distance value or the perpendicular distance is concerned, how we can do? So, what we have to do, we have to take the norm of W, that is this norm of W or W transpose, whatever you take, because it is only a vector. If you either write W or W transpose, barely means something different. And then what you do, you have to take the dot product of W with this particular point. That is what I am writing as X plus your W naught. So if I do this, I will get, let me take another page. If I do this, I will get, so W dot X plus W naught divided by norm of W. So your W is basically you have got from this particular equation, that is 1, 2, minus 2. And they have given the X as 1, 4, and 3. So the dot product is simple, 1 plus 8, then minus 6, and W naught is over here, W naught is equals to 3. So this is 3 divided by root over. We have to take absolute value of this particular vector. So it would be 1 square plus 2 square and minus 2 square. I can write it as 2 square as well. So this is 9. And over here it is uh, 6. So therefore 6 by 3 equals to 2. So this is how you can uh, evaluate the perpendicular distance. Same in the same logic, I have taken another question. This is same thing. So you can calculate by your own as well. So this is another, this would be the last question that I can take right now. So this is on SVM. So this might give you a comprehensive idea about how to deal with SVM related problems that you might see in this particular week's quiz. I have not seen that what questions they have given, but I thought of keeping this particular question into the live session. Okay, so you have two features, that is X and Y, and you have the class labels. You have either positive class or negative class. So let me first draw the equations. Sorry, draw the points. So 1, comma 1. So this is 1, 2, 3, minus 1, minus 2, minus 3, 1, 2, minus 1, minus 2. Fine. Now let's say 1, 1 is class 1. So class 1 is green class, let's say. Then you have -1, -1. So -1, -1, it is the negative class. Then you have another negative class at, okay, let's say do it sequentially. 2 by 2. So 2 by 2 is this particular point. It is also in the class +1. Then you have -1, -2, -1, -2. And the last one is 1, -1. That is 1, -1. Okay. So in case of SVM, you have seen that in simple perceptron criteria, you have a solution, you have a region of solution to choose that what would be the decision boundary. But SVM basically gives you the optimal decision boundary, which basically provides a higher margin of confidence while doing the classification. Higher the margin value, higher is the confidence of the classification. And to deal with the margin, there is another associated term that is called support vector. So support vector means, let's say if this particular line, this horizontal line, if this horizontal line is my decision boundary, let's say this line is y equals to 0, this line is x equals to 0. So this if let the y equal to 0 line is my decision boundary to segregate these two classes. So support vector will be these points. That means beyond which I cannot draw any line related to the margin. So this is the margin. So let's say I am at this particular margin. I may be at this particular margin. I can see that there is no data points from this particular class. So I can even increase the margin. I can even increase the margin at this particular point. I can see that I am hitting a data point. So till this data point, I can increase my margin. And this particular data point is basically called the support vector. Same as in this particular direction, I can increase the margin in this direction, this direction. At this particular point, I can see I am hitting some of the data points from the
Can't
other
see
class.
the drawings, like your pointers is not shown now. Only two horizontal lines I can see.
So
Now
the
I can see.
the data points you can see now, right? Like this one, this one.
Yes, 5 data points could be seen. Red,
Yeah,
two
yeah.
red and three green.
Okay, so what I was telling is basically, let's say uh, you can draw a margin over here in this particular region. Then you check that are you hitting any sort of data points? The answer is no. Then you can again increase the margin, again increase the margin. At this particular point, when you reach this particular point, there you can see that if you increase the margin a little bit out of this, you will be hitting the data point.
Right.
So you can increase the margin till the point where you actually touch the support vectors or the data points from a particular class. So these data points are called support vectors. Similarly, if you increase the margin in the negative direction, you can say you can keep your margin over here, then check, are you hitting any sort of data point? The answer is no. Then again, you can increase the margin. Then you see over here, are you hitting any sort of data point? No. But when you reach this -1 line, this -1 line, that means y equals to -1. So over there, you'll see the moment you reach y equal to -1, you are hitting these two data points. So that means this is the critical point beyond which you cannot increase your margin. So these points are again called the support vectors. And SVM corresponds to decision boundary which gives maximum margin. So this is the theory of SVM, that you can, for example, to classify these two classes, I can even draw a line like this. This can also classify. So you can see that this is a set, this is another set. It is also classifying. This particular horizontal line, this can also classify. So that means which, so this is decision boundary, let's say 1, this is decision boundary, let's say 2. In this way, you can see, you can draw infinite number of line in this region to classify these two data points, these two classes, that is class 1 and class 2. And in this region as well. So you can draw infinite number of lines. But which line to choose? That is the main question. You have to choose such a line which will give you maximum value of margin. So this is what SVM ensures. If you see the theory of SVM of this particular week. So in this particular question, they have given the data set. Given the data set, I have plotted them. Now, the question is, what can be the possible decision boundary of the SVM? So that means, as I have already told, that you can draw infinite number of lines. So they have given 4 such equations of the lines. And now they are asking that which line SVM will choose. You have to see for all these cases, which of the line gives you maximum margin. If an equation of line which gives you maximum margin, that will only be chosen by SVM as the optimal decision boundary. That is the problem. So now let us see some of the obvious equations which we can directly eliminate. One is y equals to 0. Y equals to 0 means this particular.
Not possible. Not possible.
That is not possible. Sorry. Let us start with x equals to 0. So x equals to 0 means this particular line. This is x equals to 0. So if it is x equals to 0, that you can see in one direction, you have class +1 as well -1. Again, in another direction, you have both class +1 and -1. So it is not able to classify. You are doing several misclassification. You are not able to classify them well. So that means your x equal to 0 is nullified. This cannot be the decision boundary. Okay, let it be. Then let us draw the third option, that is x equal to y. So x equal to y would be, this particular point is 1, 1. This particular point is 2, 2. This is -1, 1. So you can see that this is the line x equal to y. So in this particular line, you can see that, one second. For this particular line, you are how many of the labels, how many of the samples you are able to correctly classify? That is, this particular sample you are able to correctly classify. This particular sample you are correctly able to classify. But for the samples which are residing on the decision boundary itself, are you able to classify them?
Maybe they are identical because they are falling on the same.
So they are having same criteria over here. So that means only out of, you have total 5 samples. Out of 5 samples, you are only able to classify this particular sample and this particular sample. That means only 2 samples you are able to classify. For other 3 samples, you are not able to classify. So that means this particular line will also, it is also not the optimal solution, because you are not able to classify well. Only you are able to classify 2 samples, 3 of the samples are not able to, you are not able to classify. So that means this is also not the optimal solution. and SVM tries to find the optimal solution. Optimal solution. So because you can draw infinite number of lines over here, but from infinite number of line, SVM chooses the best line. So that means it tries to find the optimal line. And x equal to 0, x equal to y, none of them are the optimal solution. Okay. Now the next question, let's say this particular line, that is x plus y equals to 1. So we have to see whether x plus y equal to 1 could be a possible candidate or not. So if I just take one more page over here and just plot them. So this is, let's say 1, 1, then you have 2, 2, you have 1, minus 1, minus 1, minus 1, and the last point is minus 1, 2. So the last of the two options that we are left with is y equals to 0. This is x, this is y. So this particular line is the option A. So this is what y equal to 0 looks like. So please tell me what are the support vectors for this particular trace? What are the which points are basically the support vectors?
If we take the nearer points, mean 3 points would be there.
Yeah, so there would be 3 points. So I am just drawing in terms of margin. So this is one support vector, and these are the next two support vectors. So there are a total of 3 support vectors, and margin is basically sum of distance between decision surface and support vectors. And if you have a copy of support vector, for example, they are at the same location, you just omit one of the support vectors. Okay, because they are at the same position, so their effect is same. So you have to, the equation would be distance between decision surface and unique set of support vectors residing at different location. So this particular statement, unique set of support vectors residing at different sort of locations. So you can see that their y-axis location is same. So that means, and our decision surface is y equals to 0. So it is the y distance that matters in this particular case. So that means distance from this point to this part and distance from this point to this part is same only. It is the vertical distance. So that means you can omit this particular thing because their effect is same. So the total distance would be d from, so let's say this is support vector 1 and this is support vector 2. So S2 to decision surface. So let's say DEC plus distance from S1 to DEC, that is decision surface. So now please tell me what is the distance from this point to this point? This is -1, this is 1. What is the total value of margin in this case?
Margin is 2.
Yes, the margin is 2. So for this y equal to 0, we have got margin equal to 2. Now we have to see the second case. I mean the last case that we are left with. So again, if I just draw them, so this is so this is x equal to y equal to 1. So can any one of you tell me that what uh, uh, what will be the direction of the line? What would be the direction of the line? Or
Y
what point
equals
it will be
to
basically?
y
Yes.
equals to minus x plus
1
1. So
minus
down
x. Yeah.
1 minus x. That is y equal to mx plus c. So minus x means is multiplied with minus 1. Slope will be downward. And it
Yeah.
will start with y-intercept c equals to 1.
Yeah. So it would be, let's say y-intercept is 1 over here, and let's say y-intercept is 2 over here. And this will actually include this particular point as well. So the point is minus 1 comma 2. So if you put minus 1 plus 2, you can see that the output is 1. So that means this point also satisfies this particular equation of line. And this is, let's say, plus 1 over here. So I can draw the line like this. So it would, let us consider this is 1. Anyway, so this is the equation, that is x plus y equals to 1. This is how it looks like. And over here, we were able to classify all of the points correctly. You can see that at this particular side, all the data points are from single class. At this side, all the data points are from single class. That is, this is minus 1, this is plus 1. So that means all of the data points are 100. The classification accuracy is 100%. So if I choose the decision boundary to be x plus y equal to 1, just by observing this sample only, you can see that out of 5 samples, already you are not able to classify this particular sample because this is lying on the decision boundary. And what are the support vectors? The support vectors are, this is the support vector number. This is the first support vector, let's say S1, and this is the second support vector, that is S2. Now again, it is something like that. You have a line or plane, you have a data point. Now you have to calculate the perpendicular distance. So to calculate perpendicular distance, the margin, so the margin would be, this is the perpendicular distance, let's say D1, and this is the perpendicular distance, let's say D2. So we have to calculate the value of D1 and D2. So D for x plus y equal to 1 equation is D1 plus D2. And we already have calculated, given a point and given a plane or line, how we can calculate the value of distance or perpendicular distance. That is, I can consider that distance is positive distance is a positive quantity. So I can write modulus of the equation is, I can write it like this: y plus x plus y minus 1 equals to 0.
Sir,
And
what you
your
wrote here? Distance of something, the suffix equals to d1 plus d2. What is the distance of
so,
a?
so so distance, so the margin, I have to calculate margin. So this is m, let's say I am calculating
And what
margin.
is that written here? D of some suffix.
Achha,
Like what?
this one. So this is basically, let me rewrite it. So
Yes.
we are left with two last options, that is y equal to 0, that is, and another one is x plus y equals to 1. So now I am calculating margin for x plus y equals to 1. So this is just to say that this margin value is for this particular line. And already we have calculated margin for y equals to 0. So we have to see that which margin is highest. If margin is higher for this particular line, if margin is highest for this particular line, SVM will choose that one. That is the fundamental thing. So now to calculate the margin, we have to calculate the perpendicular distance from S2 to this decision boundary and from S1 to this decision boundary, which are, let's say, D2 and D1. So therefore, we have to calculate D1 plus D2 to get the margin. So how to calculate D1? So while calculating D1, what we have to do, the location is 1 comma minus 1. This is
Minus
1
one.
comma minus 1. So what I will do, x के लिए value कितना है 1, y के लिए value है -1, and then you have -1. Then root over weight का norm निकालना होता है. So the weight is basically over here. The weight is 1 comma 1. The W naught, the bias is -1. Same as the previous question. I'm just following the same formulation. So 1 square plus 1 square plus. So we have calculated D1. Now we have to calculate D2. The norm would be same because this is the line of the equation. So 1 square plus 1 square. Now we just have to see what is the numerator. The location is for S2 is 1 comma 1. So it would be 1 plus 1 minus 1. So one side it is 1 upon root 2 plus 1 upon root 2. So that is 2 divided by root 2, or
I could not understand actually. This is the first point we are taking -1, and the second one is 1 and 1.
yes.
तो सर ये अपर वाला जो आप 3 नंबर्स डाल रहे हैं 1 1 1 करके, वो थोड़ा बता दीजिए D1 के लिए.
हाँ, ठीक है. फॉर एग्जांपल जब मैं D1 कैलकुलेट कर रहा हूँ, मेरा पॉइंट है, if I go to the previous slide, D1 जब कैलकुलेट कर रहा हूँ, my point is S1. तो S1 point है at -1 comma 1. So I can consider x is -1 comma 1. So this is the point. This is the line which has equation x plus y minus 1 equals to 0, and this is the point. The point is -1 comma 1. Is it? Sorry, 1 comma -1. Sorry. This is 1 comma -1. Now to calculate the distance from this point to this line, what we do in terms of machine learning equation, already we have told you that we write equations like this: W transpose X plus W naught equals to 0. In this case, they have written the equation like this. Your X is X comma Y.
Yes, got it.
Got it? Okay.
Got it. You can continue, sir. I got it.
Okay. So in the same logic, what we have done, just let me just complete this then. So it is W1, W2, and then you have X, Y. So in our case, the W1 and W2 is 1 and 1. So this is 1. The coefficients are 1 and 1. And you have X, Y. So you will get X plus Y. And the third term is the W naught. And over here, W naught is basically -1. So you can equate it with 0. So that is why W transpose is 1 comma 1. W naught is -1. Now, while calculating the distance, what you do is basically distance equals to W transpose or W dot product with X, W dot product with X plus W naught divided by norm of W. So norm of W is what? 1 square plus 1 square. We already have seen that is the W is 1 comma 1. So 1 square plus 1 square. W multiplied with X. So our X in this particular case is 1 comma -1. So if you take dot product 1 into 1, then 1 into -1, and then W naught. W naught का value कितना है? W naught is -1. So I have written -1. Now, for this particular case, specifically, I am considering that distance is a positive. There is nothing, there is no such quantity like negative 5 kilometer, negative 10 kilometer, something like that. Distance, I am considering distance to be a positive quantity. So that is why I am putting a modulus over here. So by that same logic, you can calculate D2 as well. And if you do the mathematical manipulation, the margin is to be 1.414. So you can see for x plus y equal to 1, the margin is 1.414. For y equal to 0, margin is 2. So SVM will choose only that particular equation, decision surface, which gives you highest margin. So over here, the highest margin is for y equals to 0. Therefore, y equals to 0 is the correct answer. So this is the particular way that you have to think when you see any sort of SVM problem. What your approach should be, you have to find, if you have certain equations like this, for all of the equation, try to draw the equation. Then the rule of thumb is try to calculate the margin. And for whichever line you get the highest margin, that is the optimal line of equation that you can consider as a decision boundary. So any query?
No, sir.
So the support vectors are always supposed to be parallel to the decision plane.
Yeah. Because see, you have a equation of line. So
Yeah.
your support vectors will also be the family of parallel lines.
Okay.
For example, over here you can see that your original decision surface is y equals to 0. The first support vector for the negative class reside at y equals to -1, and this particular thing resides at y equals to +1.
Yeah.
So that means this is y equals to, this follows the equation of family, that is y equals to k. That means y equals to k is a equation of parallel lines.
Parallel
Or
lines.
family of parallel lines. Okay, so I think we can stop the session here today.
Thank
I
you for
will-
this beautiful lesson.
Yeah, thank you.
Yeah, thank you so much.
Thank you, sir.
So you can also submit the surveys as well. So in the weekly manner, you can submit the surveys as well for the live sessions. For both the TAs, you can
Yes.
submit the surveys. Okay, so I can stop
Okay,
recording.
good night from here to all the participants and to Arka, sir.